We've defined the generalization of a mass function to continuous variables. We call it a probability density function. And it all hinged on this idea that probability could be interpreted as mass, and then through that we understand that probability is also interpreted as area. And so if we want to think about it in this way, we can use the density function by way of an integral to discuss how much probability is contained somewhere. So if we are given the graph of a density function, we can determine the probability of our random variable being between these two numbers by thinking of it as the area under the graph of f. And that's just a direct extension and a direct use of what's happening in integral calculus. And so as an example, on the sheet that's attached to the videos here, there's an example where we talk about the time spoken on a long distance telephone call. And so there's a density function that's been given in this particular example. Now, we need to determine what the value of alpha is to make this a CDF, or sorry, a PDF. So that means we're going to require that the integral of the density function be equal to 1 in order for us to find alpha. Now, because the integral or the density function is only defined or non-zero for positive numbers, we are going to integrate this from 0 to infinity. And that means we have to remember how to integrate. Luckily, these types of integrals are not that bad, and most of the integrals that we encounter in this course won't be that bad. This thing is an improper integral, so technically it should be written as an integral from 0 to t alpha e to the minus x over 4 dx. So we're going to make a substitution. This is the inner part, so we're going to let u equal to negative x over 4. Du will be minus du over 4. Oh, sorry, minus dx over 4. When x is 0, that means u will be 0. And when x is t, that means u will be negative t over 4. We can go ahead and plug this into our function. And our new integral will still be a limit as t goes to infinity, 0 to minus t over 4, alpha e to the u times negative 4 du. Now, we don't know that the limit exists, but because the functions we are dealing with inside of the integral are continuous and the limits of integration are definite, we know that this integral will exist in terms of the antiderivative of the definite integral. So we could write it like this. We can't take the negative 4 alpha outside any further. This integral is pretty straightforward. We'll get negative 4 alpha e to the u evaluated from 0 to negative t over 4. And so what we end up with is a limit as t goes to infinity, negative 4 alpha times e to the minus t over 4 subtract 1, because e to the 0 is 1. Now, as t goes to infinity, this thing goes to 0, and all we are left with is a 4 alpha. And so that means we need 4 alpha to be equal to 1, and that means alpha is a quarter. So in order for this to be a density, we must have that our density function is 1/4 e to the minus x over 4 when x is 0, and then it's 0 otherwise. Now, we are going to be doing a lot with the density function, and we have to try to make our lives useful. Because a density function is defined for use with integrals, there are some properties and things that we can use from integration to help us and understand some properties of this. One of the useful properties of integration that you should remember is that if you integrate a function over a single point, so the limits of integration are the same, this is 0. So that means a single point contributes no probability, which is really weird because you're essentially adding up a whole bunch of single points, but you're getting a non-zero answer. Nonetheless, when we're talking about a continuous random variable, we can be really sloppy. We can ignore the equal to in our region. And so what I mean by that is, if I wanted to talk about the probability that x was greater than a, it's exactly the same as the probability as x is greater than a for a continuous random variable. If I wanted to talk about the probability of x between a and b inclusive, so less than or equal to on both sides, you can essentially ignore the less than, the equal to, and they will always be the same. So you can be very sloppy with a continuous random variable, but you cannot for a discrete random variable. There's a big difference. So that's one useful property that we need to worry about. For a random variable that's continuous, the CDF, the cumulative distribution function, takes on central importance. This is the most important tool that we have, and it will make lives easy when we work on things afterward. Now, from before, we defined the CDF as the probability that our random variable takes on any value up to and including x. When we talked about it with a discrete random variable, it was a summation where y was less than or equal to x, and we would add up all those values up to there. So 0, 1, 2, etc., etc. But when we talk about a continuous random variable, generally we write this as an integral, negative infinity to x, f of y dy. We are adding up the density from all values from the start, negative infinity, up to x. So we add up the density from negative infinity up to x. Now note, from the fundamental theorem of calculus, this weird expression is just an antiderivative. This is one particular antiderivative. So if we were to take the derivative of both sides of this expression, just like you should have learned about in calculus, this should end up, the derivative and the antiderivative should cancel out, and you should just get back with your density. That's really important. So why do we need a CDF? The CDF is the useful tool for calculating probabilities. How? What do you mean? If we wanted to calculate something like this, yes, it would be an integral f of x dx, kind of like that. But if we wanted to, we could think of it as this integral subtract this integral. And when we think of it in that sense, it becomes the value of the density function, or the CDF at B, subtract the CDF at A. This allows us to avoid integration. So we find the CDF, and then we avoid having to integrate again. So I'm going to show you what I mean in this particular case by going back to the example with the phone times. We know that our density function is 1/4 e to the minus x over 4 when x is positive, and it's 0 otherwise. And so the idea here is that the CDF is going to be calculated, and that means we are going to be able to integrate just once. We're going to have to integrate once. Now remember, when you do an integral with a letter in the variables, you should have a different dummy variable here. The letter you choose is irrelevant. I'm just going to choose a y. If we calculate the CDF, yes, we have to do an integration, but we only have to do it once. And once we've got it, we can reuse capital F as much as we'd like. Now, in our particular case, this is going to give us the following. Our starting integration limit is 0, and we go up to some x, and we switch the variable to be y. Now, as always, we make a substitution. We're going to say that u is negative y over 4, du is negative dy over 4. This is no longer an infinite limit, so we don't have to put a limit in front. When y is 0, u will be 0, and when y is equal to x, when y is equal to x, u will be negative x over 4. So our integral now becomes an integral 0 to negative x over 4, 1/4 e to the u, negative 4 du. The 4 and the 1/4 cancel out. And so we've now got an integral 0 to negative x over 4, e to the u du, which we know the antiderivative of e to the u is just itself. And so we end up getting 1 minus e negative x over 4. This is the CDF. You might say, Alan, I don't get it. Why did we bother doing that? This is what's called in calculus a cumulative area function. It calculates all the area from the beginning limit up to and including x. And that's the important thing here. Now note, if I were to take the derivative of this thing, I should use the chain rule, and I would get 1/4 e to the negative x over 4, which is equal to the density like it's supposed to. So I'm very happy about that. That does exactly what I expected to do. So what do I do with this thing? Okay, now that I've got the CDF, I use it to make any sort of calculation that I want. And so on the sheet, the example that you've been asked for is saying, calculate the probability that this random variable will be between 7 and 12. Well, now this becomes no longer an integration problem. We could sit there and do the integral with limits from 7 to 12, but every time I change the numbers, I'd have to redo the integral. So why bother redoing the integral? Why not just do it once and then use the result that I get? And it turns out that this approach is great when you can get a function for your CDF. If you cannot get a function for your CDF, this becomes a lot worse. But nonetheless, it now becomes a simple matter to go ahead and calculate things like this. And depending on the kind of question that you've been given, it just takes a little bit of time to think about what's going on. So for instance, if I wanted to talk about part D, I'd get something like this. And just by definition here, this would be the CDF function, right? F of 7. So it would be 1 minus e to the negative 7 over 4. If I wanted to calculate the probability that x would be greater than 12. This, in our language, is exactly the same as 1 minus the probability that x is less than or equal to 12. So this would be 1 minus the CDF at 12. So this would be 1 minus e to the minus 12 over 4. So this would just be e to the negative 3. So things of this sort become really, really straightforward to use. And once you've got the CDF, then you've got one calculation, and that's all you need to do.